Is it electric and magnetic all the way down? I don't know.
Okay.
So, don't mind the little bit of Elsa in the background there. That's not the point. But the point is, I had a question. I'm sitting there, I think that was the first time at the monastery, and doing a little presentation trying to reiterate what I claim to believe that I might know about what's going on based upon the HF8 model, yada, yada, yada. And I keep on noticing it's like, is it electromagnetic all the way down? What's the deal with charge? As was the name of the video and everything. And more recently, I started looking into some other things, exploring the Internet of Stuff and Things, and yeah, electricity. It's what allows us to do modern stuff and things. How does it even work? Well, maybe we'll find out sooner than later. You all know what that means. We conjecture ahead.
Although this is going to be weird, and it's going to be about a different.
Title of the conference was something like "Ground Truth" or "Turtles All the Way Down," and so it seems as though there's one Ruliad. I don't think it rules them all, and it might be just hyper-rulial turtles all the way down.
Yes, it's on the back of an infinite number of hyper-rulial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
Hey guys, what's going on? Memes here. So, again, when the old noggin gets a jogging, sometimes you just gotta explore a little bit for your own sake. But one of the things, we did a video on this before, it's like, all right, so what happens, let's say we take, we go to our friend Wolfram Alpha here. And let's take, I don't know, the speed of light, we square it. Let's type it, oh my god. I'm sorry, we're still on full screen. There we go. We're back in action. All right, you take c squared. No, we want to use it as a unit. Okay, the speed of light squared, we get that. That number, what I noticed from Fractal Woman was like, it seems to be of the same, at least number, the Coulomb constant. It's very interesting. And then when you multiply it by the magnetic constant, let's say, I don't know, the Planck length times the Planck mass. When you divide it by the Planck charge, you square it, but you put a -2 in there, so it'll go in the denominator. Let's go through our speed of light, blah, blah, blah. So we multiply. Oh. It comes out to be 0.988 times 10 to the 9 meters per farad, or 1 Coulomb constant. That's inverse permeativity, according to Wolfram Alpha, because now we got certain dimensions there. We got time and current, and charge is basically a derivative of or current is a derivative of time and charge. So, I mean, again, that's very interesting. But what are we talking about? Links to stuff and things in the doobly-doo below. So, we go over to our friend Wikipedia. Take it for what it's worth. We're back to vacuum permittivity. Commonly noted E naught, pronounced epsilon naught or epsilon zero, is the value of absolute dielectric permittivity of classical vacuum. Wait a second. Hasn't Kali been saying there's some dielectric material, perhaps a superfluid? As I discussed with Mr. Goldstein, it's totally not the ether. Or the distributed capacitance of the vacuum is an ideal baseline physical constant. Ooh, its code-out value is yada, yada, yada. Okay, that 8.854, yada, yada. We got it to like, I don't know, 10, 11 significant digits or so, times 10 to the -12 farads per meter. Oh, that seems to be a bit of an inverse of the other thing there. Is a measure of how dense an electric field is permitted to form in response to electric charges, and relates the units of electric charge to mechanical quantities, such as length and force. Wait a second. It relates length and force. Force equals mass times acceleration. That's That's mass, which is also then acceleration is, what is it, length divided by time squared. It's length per time, right? Oh, that extra unit in there makes a difference. Apparently, that's also how you get momentum and stuff like that. Interesting things happen when one is under acceleration. That's what seems to be the case. But okay, so we go through. Okay, we go through that, and then we have Coulomb's law, and we've done the electric and Coulomb constants as well. And again, they redefined SI recently. So the ampere was redefined. Redefined by defining the elementary charge as an exact number of coulombs, as from 20th of May 2019, where the effect of the vacuum electric permittivity is no longer has an exactly determined value in SI units. What? Oh, some of those other things they set to like about 10 significant digits because they're like, this is exact. We have the high level of confidence in our current measurements and everything. Okay. The value of electron charge became a numerically defined quantity, not measured. Oh, okay. So then we set a limit on that, making mu naught a measured quantity. Coincidentally, E naught is not exact. As before is defined by the equation, E naught is 1 over the magnetic permeability times C squared. Wait a second. Magnetic permeability, C squared. Wait a second. What happens if we toss a 1 over it? Oh. Huh. The Coulomb constant. Wait a second. But we still had the Coulomb constant. I totally must have done something wrong. What did I do? Oh, we forgot to divide. Boomer. All right. But wait a second. It's 12.57 electric constants. That's not one constant. Now, when one spends enough time on Wolfram Alpha, and you spend enough time with numbers, occasionally start to notice things. 12.57, that sounds familiar. Might there be a particular number that we use that might get, okay, oh God. All right, so what if we did 4 pi? What's that equal to? 12.56, that looks pretty close. All right, we'll go back to whatever we had there. So what if we took that, take that whole thing, we protect ourselves, our mathematical save point. We put brackets onto it so we won't mess around with other things on it. That's how I like to think. It's better to have them and not need them than need them and not have them. I've heard that somewhere. We divide by 4 pi. Dun, 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 dun. Oh, looky, one electric constant. It's like some digital wizardry right here, using the maths and everything. It's okay. We have the computers to do the different. You just try to pay attention to see what's going on. All right. So maybe that's why the whole Coulomb's law is based upon like spherical charge-based points. I don't know, balls or something like that. That's what I generally take away. But hey, Disney, what's going on, my man? Dude, all we're talking about, dude, it's literally just magnets. It's like, all right, you get a magnet, you get 2 magnets. If they're opposite magnets, they don't want to go together. This is just basically it's almost kind of like the whole vacuum. It's like, is there even a true vacuum? We call it empty space. Is there any true vacuum? Is it like the whole, like, no true Irishman? I believe I'm part Irish, so I believe it allows me to get away with saying that. But it's one of those things where it's like, if we're saying, well, there's quantum fluctuations. So it's not actually a vacuum. There's stuff going on there. There's like different things happening, okay? It's almost like there's a force permeating through all things. That's why the whole Star Wars, the Jedi thing, that kind of talks to me. I prefer to believe that gray is the way, but that's a side tangent on other things. But we'll get back to the sciences. So it's just very interesting that these things, like literally, you don't even need to do all the numbers. You literally just type in what it is. That's the beauty of Wolfram Alpha. It's a computational knowledge engine. Or if you're just trying to find like ticket prices or stuff like that, I mean, it probably points you in the right direction. I'm not sure about ticket prices. I might be lying about that. But so again, here we get into what we were just talking about. Again, according to our friend Wikipedia, the terminology. Historically, the parameter E0 has been known by many different names. The terms vacuum permeativity, or its variants such as permeativity in/of vacuum, permeativity of empty space, or permeativity of free space, yada, yada, yada. So they go into all the different parameters, but we don't need to delve into that. You can read it. There's a really cool thing that even on the Mystify Psi, Anastasia had brought up. Shout out to the Mystify Psi podcast. But Coulomb's law. Here's the thing. It's like, all right, you get two charges. If they're the same, they go different ways. Cool. If they're different, they come together. Groovy. And it's literally, you just take the magnitude of whatever it is, and that's going to derive whatever, like, the force is. And that's pretty freaking neat. So, there's one little thing here. I haven't gone through the calculation to go through, but okay. This is according to them. I haven't derived this. Take it for what it's worth, but this is just a fantastical thing. 1 second's worth of charge from a 120-watt light bulb. So you take 2 light bulbs, you run them for 1 second, they're 120 watts. How many coulombs would you have gone through? Assume you have 1 coulomb of force each. That's negative because Ben Franklin, Ben, you had a chance. You're like, all right, it's a 50-50 shot. Am I going to call the electron and the stuff it does positive or negative? All I know is if any of that kite story is true, if I get zapped by lightning while flying a kite, I'm going to view that as a very negative experience. Just my personal opinion. Psst, he got it wrong. I'm not saying that affects anything with the sign convention, but I don't know it doesn't. We continue. But okay, so you got 1 coulomb and 1 coulomb of differencing. All right. At 1 meter, it's 1 million tons of repulsion. What? And they go through here because it's about 9 times 10, or that 8.85 whatever times 10 to the 9 newtons per meter squared. That 1 coulomb and 1 coulomb, and a ton is 2,000 pounds of force. You get over 1. That's crazy. And I think that's also how like nuclear weapons end up working or something, because the nuclear force, or the strong force, is about like another 137 times stronger than that, which is absolutely crazy. Also why nuclear power, dude, I remember back in the day, what was it? Freaking, even like history class or something like that, or so, whatever it was, like they had this picture in the textbook. And again, state-run school for the win, whatever you want to think about that. But it's like, all right, so, all right, you get 1 ton of coal. That's equivalent to, I don't know, 100 barrels of oil. Okay, that's more efficient. And it's like 1 gram of uranium equals 1 ton of coal, 100. I'm like, that sounds more efficient. Now, you want things to be safe. You don't want a 3 Mile Island. You don't want a Chernobyl. You don't want a Fukushima happening. Yeah, those are terrible. That's why you want to have different safety redundancies upon redundancies upon redundancies. Yeah. And if we can break fusion, I don't think we need to worry about that anyway. We're getting closer, I claim. But, so what the heck is the point of all this? All right, we go to our friends again. Well, from, hey, Jensen, what's going on? And awesomely, yes, squirrels are known for having apparently excess energy. Don't rub them against a balloon, or don't, oh God. Squirrels are people too. But, all right, we got our electric constant. So that's basically what we had already done. The magnetic constant, which actually, I think that's why I left it here. Again, this is one of the big things, and this is actually, going through this now is actually giving me a bit more confidence in the monastery's model, just because it's like, all right, you don't need to do the math, you just need to know the claim is we've got stuff doing things, and that leads to our existence. Okay. Now, there might be some complex stuff in order to get up to us for some random dude on the internet that kind of tried to chop through his leg accidentally yesterday with a machete. Oh God, I should post a picture. No, I shouldn't, but I will anyway. But all I know is the claim is, what's the stuff of our own persistence? You got 5-dimensional ingredients: time, space, charge, mass, and temperature. When one goes down the Wolfram hole long enough, and you break down like that current and everything, because current is basically, all right, it's time and charge and everything. It's like, okay, it's a derivation, but essentially, aside from something dimensionless like the fine structure constant, yeah, everything else within nature is made up of 5-dimensional ingredients. It might be complex derivation, but all these things we're looking at, they're made up of 5-dimensional ingredients. And again, to be fair, they had the fine structure constant in there as well. If only we could find a geometrical way of deriving that, that may help. I digress. But what are we talking about here? So in order to get to that magnetic the magnetic constant, which coincidentally, or is the magnetic permeability, pardon. I think we already did this. Planck mass, Planck length, and Planck, I can't even spell, charge squared, but we wanted the denominator, so we just put a little minus sign in front of the 2. Gives us this. We wouldn't need to say multiplication because that's apparently a weird thing to Wolfram alpha. Okay. Oh, look. The magnitude is exactly 10 to the negative 7. Oh, very interesting. Oh, it comes out to be an Amper's constant. Or a Biot-Sievert constant. What's it characterized as? Oh, magnetic permeability. Do we have any other things, Wolfram alpha? Incremental permeability, magnetic linear inductance density. I have no idea what that is. That sounds fantastic. Sounds kind of like a turducken. All right, magnetic permeability. All right, we call it electromagnetism. There seems to be a balance here because anytime you have like an electric field, one of them is going to be at 90 degrees to each other. Why? Why is it all of a sudden, all right, if you get an electric charge or you get a magnetic charge, like one ends up causing the other? And that's why I'm like, okay, working with a model that's basis is essentially the complement of the figure 8 knot, the hyperbolic figure 8 knot. So what the heck are we talking about? Well, let's just do this. We'll go, I'll go back over here. So go back to our friends YouTube. Boom. All right. So, oh, look. Godzilla in my feed. Imagine my shock. Godzilla anime and a whole bunch of science videos. The terrible thing is at one point, like, I'm going over, it's like, all right, you got this complicated thing doing like this. I'm like, that reminds me of Naruto generating a Rasengan. And I'm showing that the video of, like, OG Naruto. He's like, oh, you can, like, learn physics from anime. I'm like, I wouldn't say that. But it's like, that's why it's like people telling me this complex action that gives rise to a hypersphere and all these vectors. I'm like, so it's a focusing of energy going in a particular direction and concentration state. Okay, it gives rise to a hypersphere of some form of energy. Those are things I understand because I've watched so much anime. Not enough, I claim. But what were we looking for again? Oh yeah, so hyperbolic figure 8 knot. No, not with a K. With a K. Professor Henry Segerman. All right, so hold on. We need to go back. We don't really need the sound, but I just want to show this. Figure. Henry. I know I can just go to his channel. I feel like this is important for if anybody's actually okay. So we have the symmetric figure 8 knot. So the whole claim is, to my best understanding, is this is essentially the knot. This is a projection in 3 space, or basically our 3 dimensions. So basically, that's going to be balanced. You can project it out however you want, but there's an action going on in there, which gives rise to the complement. And the complement is everywhere that knot isn't. So that knot's doing a crazy thing there. It gives rise to this. And again, this is those cutouts and everything are just for us to basically see through and kind of see what's going on there. Like it would actually be like a solid surface, if you would, because you got this crazy amount of energy doing these things, and that's everywhere that other object is not. See what I did there? Unintentional irony. But we have this, essentially that kind of hovers around a particular point, a 0, 0, 0, 0 point. Like literally on the coordinate map, when you go onto Wikipedia, it goes around the 0, 0, 0, 0 point. I'm like, so that, at least coordinate-wise, again, I'm not a mathematician nor a professionally trained physicist. I'm a dude on the internet. It kind of sounds like a singular point. Now, nothing ever actually totally gets there, but there is at least a localized singular point, if you would. If everything's going around that point, might that explain a lot? I don't know. I don't know. I'm just taking a shot in the dark here. Okay. So we got those objects, but we also have, what are we talking about anyway? We're talking about electromagnetism and all this crazy stuff that's going on. And apparently, where is it? We started having things like 4 pi and stuff getting there. What is 4 pi? Well, that, like 2 pi is basically like a circle. 4 pi is basically like a sphere. Wait a second. A sphere, you say? Huh. Now, if we filled in those gaps and didn't allow ourselves to see, and we projected it in not a kind of donut form, that could be projected as a sphere, no? Oh yeah, it's also made up of 2 of the minimal non-orientable manifolds, the Giesking constant, that has the minimal volume that's above 1, and yeah, they're made of 2 idealized, or each one is made up of an idealized. Let's just go to it. So, Giesking constant. Oh God. Yes, don't mind me trying to be like a knockoff Professor Wolfram here, except he does it like without even using his own tools. He just says it off the like, I think we all had one of those friends that was basically like our Wikipedia friend. Like, you just ask them a question and you're going to get some form of an answer. Maybe they don't know. They'll point you in the right direction. But like before Wikipedia was a thing, we had the internet. Like, I feel like we all had like that one really smart friend that like knew all these facts and everything, or at least how to go about them. I feel like the process now is quite important. Hey, Dan. Now, here's the thing. The cellular automata, I think those are actually probably going to emerge, and they'll probably be some of the easier thing as well, because you can actually visualize it. I'm not saying that the simplest Turing machine going through doing its things may have a computational equivalence to our colloquially called universe. I can't say it doesn't. Again, this is rampant conjecture on my part here. I'm seeing some, but then again, I lift things up, and well, technically, I think I might be done now after a small injury. Now this is going to be my last week anyway, but yeah, it's very interesting there. So what are we talking about? Giesking manifold. Don't worry about any of that. All you know is the number is a little greater than 1. Okay. It is the, in mathematics, the Giesking manifold is a cusp hyperbolic 3 manifold of finite volume. It is non-orientable and has the smallest volume among non-compact hyperbolic manifolds, having volume approximately, about 1.0149, yada yada. It was discovered by Hugo Giesking in 1912. The volume is called the Giesking constant. It's got this cool thing here. So you get some very interesting value. Oh, it's the Clausen function. How fancy. I know Thad went over that, but the Giesking manifold can be constructed by removing the vertices, so the pointy parts, from a tetrahedron, and then gluing the faces together in pairs. using a fine linear maps. Label the vertices, blah, 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 and then you glue the vertices in that particular way. It's very interesting that the smallest platonic solid happens to lead to the smallest non-orientable manifold, 3-manifold, non-compact. The angle made by the faces is pi divided by 3. I mean, that's cool. Which also, the Giesecke manifold has a double cover homeomorphic to the figure 8 knot complement. Oh, that thing that Professor Segerman was showing us, that kind of like spheroid thing that could be projected out there. Oh, very interesting. The underlying compact manifold has a Klein-Bottle boundary. Wait a second, that's that thing that like flows into itself. I've heard certain folks say, I don't know, depending on the geometry of our realm of persistence, maybe it's flowing into itself. I'm paraphrasing here. Again, rampant conjecture on my part. And the first homology group of the Giesecke manifold is the integers. Wait. The integers? Those are the numbers, right? So wait. So what you're saying is this object of the HF8 model, or the minimal arena, is using a double cover of the minimal, non-orientable, non-compact 3-manifold. Is a Kleinian-Bottle structure kind of flowing into itself. Its first homology group is the integers, and it's a double cover of each one going a different way. You can't make up reality. I'm just saying. Oh yeah, and the Giesecke manifold is a fiber bundle over the circle fiber of the once punctured torus Mandromedy of yeah. There's a lot of cool things, and again, is that reality? I don't know. All I know is it seems to, the claim is, reproduce the constants of nature, and by using a coherent set of units, seems to transition us up to about 14 significant digits to general relativity, and gives us some more predictions. It's got 2 more confirmed predictions in string theory right now. Well, 3 if you consider the second time you do the muon, because in the second published work, like source code 7 predicted the muon G2 results back in 2021. The second edition of Thad's book 44, we just did the equation the other day, basically fell within the lesson because they halved the error bars. Like the old prediction actually would have fallen out of it. The new prediction, it fell squarely within the error bars. So I mean, if you count that as an extra prediction, you could say there's 3 more confirmed predictions in string theory, but it's the same thing. So it's like, yeah, you'd rather, I don't know. I just thought it was interesting when we looked at the old prediction for the classical electron radius. We're looking at the new data. Oh, we got like 2 or 3 more significant digits. I'm like, oh, that was a prediction. Groovy. And then we found something more beautiful, because you want to hone in on the best things. Well, that's how we discovered the imaginary goat ratio. Still need to do a video on that, but LBG, what's going on, my dude? Thank you for joining my friend. I still need to reach out to you for other things, brother. I apologize. But all right, so we got all that. Okay, so let's get into what the heck I actually wanted to do. All right, so you got these numbers and everything on NIST. Yeah, Coulomb's constant there, so that's got that 1 over the 4 there, yada, yada, yada. And then it's one of those things where you start to notice. These are, don't worry, we don't need any sound for this. This was what? A geometric derivation of the electric constant. It's one of those things you start looking at this. Okay. The big thing that I notice is, okay, you got Planck times squared, TP. So basically, the sub P is basically just means Planck. So Planck times squared, that's the Planck charge squared. And that's all over the Planck length cubed and the Planck mass. Okay. We go over here, a geometric derivation of Coulomb's constant. So we have the electric and the Coulomb constant. What's this? The Planck length cubed. That's the Planck mass divided by the Planck time and the Planck charge squared. Wait a second. the numerator and denominator are flipped. In the electric constant, you got that 1 over 4 pi thingy there. And oh, look, in the terminal action, because the whole construction of all this jazz is basically the stuff doing things. What's the stuff? We got our dimensional ingredients. What's the thing it's doing? It's 1 over 4 pi. That's whatever action that happens to be for its primary action. For our other friend, the thing it's doing is 1. It's literally just 1. We don't show that there, so it can be confusing, but the action is just 1 for these dimensional ingredients. This is the stuff we're working with. It's doing a 1, whatever that may mean. And then the back side, we have the terminal action, because right around 10 to the 7 decimal places, or right around, what is it, the magnetic flux? Oh, yeah, what do we call it? Magnetic permeability, at 10 to the negative 7. Yeah, things start to get a bit wonky right there, because sometimes before, sometimes after, usually right around 7 significant digits, our calculations seem to kind of go askew, and I'm not saying that that's one of the reasons why we had to redefine SI back in 2019. Well, a lot of really smart people thought it was important, and they're smart people. But, okay. So the electric constant, we got 1 minus 4 pi over j theta to the 4th times that little box thingy right there. That's literally like this right here. It's that 10 to the negative 7. We just take that magnitude right there, 10 to the negative 7, because we figure right around that border, something's usually going awry. So that's why we have it in the backside action. Some may call it a correction term, well, call it whatever you will there, but it seems to be coherent and consistent. So we got 1 minus 4 pi over our j theta there. We got 1 plus 4 pi. Oh, very interesting. So again, that's just really cool. So when you go into different things like this, we're going to wrap up here in just a second. I know we've been blathering on, and we're actually going to get into the most interesting things here, which we'll save the most salacious claims for the very end. It's not even really my claims, but it's starting to make sense to me. I'm not saying it's right. Okay, so we have, let's go back. Where are we? Okay, so do our friend here. Okay, so we had that 12.7, blah, blah, blah. We move ahead. Basically, as soon as you divide by 4 pi, you get your electric constant. That's cool. And then over here, we have, what is this? Oh, the interesting thing. So, all right, basically we got Coulomb's constant there. So what is that? Planck time. Okay, so Planck length cubed, Planck mass, blah, blah, blah. We already went into that. Gives us that 10 to the 9. And then when you multiply those two things together, those two previous things, the interesting thing is, maybe it's just because you get the inversion, you get 1. Now, again, maybe that's just obvious because we're just taking the flips of the dimensions there. I just think it's very beautiful that it adds up to 1. 1 what? I mean, I may have some ideas and everything. I don't necessarily know. I just think it's really neat that it happens to add up to 1. Oh, and now for the most salacious things. Can't forget. Again, shout out to Shiloh and Anastasia from the Demystify Side podcast for having on some of the folks from Quisicle. What's that mean? It's like basically the quantum bicycle project. So, which, again, intuitively, from like, if you're trying to have like a materialistic view, it's like, how can I view this rather than it's like, there's a probability of this and that might happen here. It's like, all right, what if we assume there are fibers or waves of force flowing through the different stuff and things of our realm of persistence? But essentially here, and again, I could be getting this all wrong, but the claim is the whole strong nuclear force is basically electrostatic repels. until it gets so close, and then the strong force takes over. They're literally, it looks like they're saying here, once you get so close, these spherical lines of force are literally just catching each other. I'm like, wait a second. Are you literally saying the strong force is just basically the electromagnetic force just at a particular length scale, and that happens to work out here? And apparently some people are doing research, and it might be that. Again, here's some I haven't verified these calculations. I was just listening to them. I'm like, all right, because what is it? Strong force only kicks in right around like 2 femtometers, which 10 to the negative 14, 15 meters. You got ridiculously small places. And then it's like, I'm just thinking, I'm like, all right, so we got all these waves of force. They're repelling, but what happens when you get in with a certain round? If you're going to consider it a point charge, like there's going to be some 0, 0 or point of 1 where you're looping around. If you're already to that point, like what like would you bind together? I mean, and then to split that, I mean, you're going to have a different like energy scale, and you might see those other mesons and everything, or whatever those other force carrier particles are. I'm just like, I mean, is like, would that be like why gluons do the thing they do? It's literally just a line of force, except it's like it's keeping it together rather than like repelling it apart. But but what about protons and electrons? They should just spiral in. I'm like, well, then again, I hear folks, and again, this is just rampant conjecture on my part. I've totally gone off the deep end. I'm not saying any of this stuff is true. It's just these are the things going through my mind that if there's some semblance of potentially being true, or even if it stimulates another person, older, younger, watching temporally now or in the future, a smarter person than myself, maybe it gets their old noggin drawing like, well, memes is totally wrong, but it got me to thinking in a slightly different way. And if we happen to do this, maybe this would work. Why? Humanity needs to win, I claim. But I'm sitting at this, I'm like, all right. So I mean, if this was the case, I'm like, it kind of sounds like they're saying that the force of electromagnetism may account for the strong force. I mean, at that point, we're kind of talking about the same thing in different ways. And there also was, maybe Professor Feynman just misspoke, or maybe I misheard it, but I'm pretty sure at one point he said atoms are made of electricity. And it just went on with the conversation at one point. I'm like, now, yes. Now, was he saying that was its only component? I mean, I was probably just hearing what I wanted to hear at the time, but I just found it interesting. You've got some other smart folks over here saying some different things. It's like, I mean, would this just simplify what's going on? How do you get closer? You need high temperature. What do you need? You need a lot of jiggling atoms and stuff like that to hit a particular temperature for the point where I believe the electromagnetism actually declines, because apparently the fine structure constant isn't even necessarily constant, because once you get up to a certain temperature, it doesn't necessarily even matter, so to speak. I'm just like, well, if you have that point where they get together, and if all of a sudden you have some form of whatever considered billiard ball, whatever it is, or they're kind of grinding together, might that slow down some of that jiggly temperature motion, and the electric field ends up just kind of locking back in, and at that point you're already kind of together rather than like trying to bump off each other. You're like, all right, we're already here. It's kind of like, how close does it need to be for the fist to be able to get like a good grip on it? And again, just rampant conjecture on my part, but I just find it interesting that you just go in here and you just throw in some of these numbers here. You just throw it in just because I think we start off at the beginning here. Yeah. You just start off with this. All right, we got the electric constant, but if we literally just put 1 over c squared plus the speed of light. Hold on, let me go back twice. Boom. Okay. All right. Oh, wait. Too far. All right. Coulomb constant. C squared. Again, c squared, you look at that. That's right about... That looks like the Coulomb constant. And then once you add in that magnetic permeability, you get the Coulomb constant once the speed of light squared is added in. Literally, the dimensions just add up. Like, what? I just think that's pretty neat. And if we can learn more about what might actually be going on, and I say the sky's the limit and space is the place. Ooh, yeah. I need to work on that. But yeah, that's all I really got right now. Just rampant conjecture from a crazy person on the internet, but I'm a crazy person that's been blessed enough to speak with some really smart folks, including some who may be watching now or temporally in the future. But that's all we got for right now. Take care of yourselves. Peace out, everybody. It's a wacky and wild world out there, but it's hoping for a better tomorrow. Take care of yourselves.